This video is going to be about banked curves. I'm hoping that you watched one of the previous videos about what a banked curve looks like, because it's much easier to see in a multiple angle type of situation. If you haven't, go back and watch that right now. But if you have, then let's move forward. The idea of a banked curve is that we have some kind of a turn, and because we are going to take this turn at a pretty reasonable speed, we want that turn to be banked. So we're going to have, imagine driving in the inside of a cone, and this thing loops all the way around this way. So there is the road. Maybe this is your lane. And there is an angle of inclination of this curve. So what we're doing is looking at your car. So this is kind of looking at the back of your car. There are the tires. So this is a back view of your car. Your car is going to make this turn. I hope that makes sense. For this first case, we're going to look at this without friction. So maybe this is an icy day or a rainy day, or maybe you are designing this road and you would like this to be safe even under the worst of conditions. We're going to look first with no friction, but then I'll bring in a separate video that looks at including friction. What I've got right now is something like this. Here's my car. Here is the angle of my incline. And I'm going to free body diagram this thing. I'm going to leave the car right now as just having an unknown mass m. And I'm doing that because I'm hoping, I guess I know ahead of time, but it is the hope that the mass wouldn't matter. You don't want to have to design a different road for a light car versus a heavy car versus a semi-truck or something like that. You'd really like this to work for all cars right away. So hopefully the mass doesn't matter. We have downward mg. We have a normal force that points perpendicular to the road. And if we don't have friction, that's really it. But now here's the tricky part. We are turning. We're not moving up or down the ramp. We are turning. So when we are at this location, we can say relative to the center of our circle, that's our radius. As we turn, as we make our way around the turn, we are going to stay at that same radius. So when our car is here, it seems this wanted to fix that. When our car is here, we are still at that same radius, at that same height above the bottom of this, which means our turning, our actual motion, we're going to get an acceleration that points this way. Even though we have an incline, we're not moving up or down that incline. That would be a problem. Our turning radius is in a horizontal plane. And this is really the trick to banked curve problems, is recognizing that we are on an incline but using regular axes. So there's that part, and then we know that our acceleration has to be this way, and it's toward the center of a circle, so that's going to be a centripetal acceleration. That will be our free body diagram. Now the sort of question that we get with this is usually something like, find the maximum safe turning speed. Here we go. I'm going to have to break a vector into components. Now my horizontal, or my x-axis is horizontal, so this time it's this force, this normal force, that I have to break into components. The angle of my ramp has to be the same as the angle in here. So this side is going to be an n cos theta, This side is going to be an n sine theta, and I don't know what my normal force is necessarily, so maybe I will leave those in red. When I do this, I'm going to say I have a sum of forces, and I'll do both of them. So let's do y first. In the y direction, I have normal force times cosine theta. That points in the positive y. I have mg in the negative y, and that equals mass times acceleration in y. In the y direction, I had better not be accelerating. So I can solve this thing and say n is equal to mg over cosine theta. Great. Now the x direction. In the x direction, I have just n sine theta. And that's going to be equal to mass times acceleration in x. Acceleration in x, that is a centripetal acceleration. And that's going to be equal to v squared over r. So I have my normal force. I can plug that in here. That gives me mg over cosine theta. That was my normal force. Times sine theta equals m times v squared over r. I'm looking for that speed. Here's m, those can cancel, and that's great. Now my curve is going to be able to be designed the same way for a Volkswagen Beetle as it is for a semi-truck. Pretty good deal. I've got a sine over cosine, that's going to become a tangent. So the left side becomes g tan theta. The right side is just v squared over r. I'm solving for v. V is going to be g r tan theta, all under a square root. I will do a separate video in just a little bit with an example that runs through this whole thing with numbers. I guess I can run through some numbers right now. Let's give this an angle of inclination of 10 degrees. We can give this a radius of 20 meters, and that's enough to be able to solve. So 10 degrees and 20 meters. In that case, if theta equals 10 degrees and r is 20 meters, which is a small radius for like a freeway turn, then we are going to get v equals square root of g r times the tangent of 10 degrees, and we would get about 6 meters per second. 6 meters per second works out to be a little more than 12, about 13 miles per hour. This is a low speed turn, but to try and turn in a 20-meter radius, that's pretty tight, and to do that without friction at all, you're not going to be able to take that turn very fast. So that's a banked curve with no friction.